Hi everyone. In this video I'll be going over 6.1 and 6.2. 6.1 is about areas between curves. So this is where we're kind of kicking it up a notch, where there's going to be not just one function, but there's potentially going to be two or more functions for which we're going to find areas between. All right, so rather than just finding the area between the curve and the x-axis, we might have that there's another function happening and we want to find the area between those two curves. So just as a way of explaining the ultimate formula that we're going to use, let's look at a couple preliminary examples for which calculus isn't really needed. So if you want to find the area between the curves of f and g, where f is this constant function 6, g is this constant function 4, and we're going from 1 to 8. So let's try to find the area between those curves. Maybe I'll do this one in blue. So between 1 and 8, so I would have this function here. Right? And this function may be in red. Okay. So what we would be looking for, like the answer, the area between the curves, would be this area here. So one thing I could do is find the area below the dark blue curve, right? So I could say, okay, the area just under this darker blue curve would be, well, this is a rectangle of length 8. So I'd have like an L times W situation, this rectangle with length, I guess it would be a length 7 technically, right? 8 minus 1. So that's a length 7 times, we would have a height of our function 6. So that would be 42 square units for that darker blue one. The area under the red, again, it's a rectangle, right? Going this way. And it still would have a length of 7, but this time it has a height of 4. So we would have 28 square units there. In order to find the space between, so the area of the thing we actually care about, what I could do is take the upper area and subtract away the lower area. So I'm going to take 42 and subtract 28. 14 square units, right? And you can verify that also by just looking at the literal area of that rectangle, right? It's a length of 7. It's a height of 2. It goes from 4 to 6. So that 7 times the 2 also is another way of producing that 14. So what I did was I took the upper and I subtracted the lower. Meaning this is our one above, this is our function below within this interval. So I took the upper minus the lower and I got the actual. Let's try another one. So what if these are the functions we care about? We're going from 0 to 10 this time. So it says, find the area between the curves. We have y1 equals this square root, and I have y2 equals this other square root. If you square both sides, you would get y squared equals 25 minus x minus 5 squared. If you add this over, we could write x minus 5 squared plus y squared equals 25. So this first one is actually, since there's only the plus side, it's actually the upper half of a circle centered at 5, 0 with radius 5. Right, we would have a center here of 5, 0, and then r equals 5, the square root of 25. But I'm only going to plot the upper half because it was just the positive square root. So right here at 5, 0, we have that center, and then I go a radius of 5 away to the right, left, and up. So we have that semicircle. That's y1. And then for the one in red, similar stuff is happening, right? If you imagine rearranging, I'm still going to have the center be at 5, 0. So they actually are concentric semicircles. They share the same center, in other words. But for this one, it'll have a radius of 3, right? We got 25 led to a radius of 5. The square root of 9 is 3. So from that center, I would go 1, 2, 3, 1, 2, 3, 1, 2, 3. And this would be, again, the upper half of this kind of smaller semicircle, right? And find the area between the curves, meaning this area here. So what we would do is, again, I would find the area of this outer function, and it's another kind of finding what you're looking for by taking the difference, right? We took the difference, the upper minus lower here from before. That's what we're going to do here as well. So the area of that upper one, well, that's a circle of radius 5, but it's just half of that circle. So it'll be pi 5 squared over 2. In other words, it would be 25 halves pi square units. Right, pi r squared for a circle, and then I'm cutting that in half for this semicircle. The area of the smaller one, right, this is now a radius 3 semicircle, so I'd have pi r squared and then again over 2. So I'd have 9 halves pi square units. The area of the actual thing that we care about would be equal to that upper area, right? That's the area all throughout. So I'd have 25 halves pi. But then to find the true area, this light blue region, I need to subtract 9 halves pi. So again, that's this upper minus the lower. It looks like after doing that, we would have 16 halves, which is 8. So we'll have, in the end, 8 pi square units. So those are a couple examples where we didn't actually need calculus, but the idea that we're using here is really the idea of what we're going to do with calculus. So keep in mind, if you have the integral of some function over this interval a to b, that this is the area under the curve, right? So this is the area under, or I'll say between, f and the x-axis. So how can we extend that to if we have two curves and we want to find the area between those curves? So that would be equivalent to the integral from a to b of the upper minus the integral from a to b of f lower. Okay, and that's summarized on the next page. So down here on page 126, this is what we're going to be doing. So the area of a region bounded by curves f and g from lines x equals a to x equals b, where f and g are continuous, and the assumption is that f of x is greater than or equal to g for all x in this interval. So the larger function needs to come first to find the area between the curve in that interval, right? So it may be sometimes that your functions switch. We'll see what happens on this one in a second, but imagine you had like a function f. Let's call this f, that one in blue. And let's say you had another function g. And let's say this is your interval, a to b. If you want to know this area, then notice that there's a switch, right? There's some point right here, C, such that where F was above before C, F is now below after C. So you would have to do two integrals where you go from first A to C, where you have F minus G, and then you would add to that another integral going from C to B, where G is now being subtracted from by F. Okay, let's try an actual one involving calculus here. All right, it says find the area between the curves of F, and F is this quadratic, negative x squared plus 6x. And G is also this other quadratic, x squared over 4. So what I'm gonna do first is just plot this thing. All right, so I'll go ahead and plot this one in blue. And then eventually I'll plot this one in red. So just to do this, it looks like we'd have at x equals 0, we'd have a 0. So I just plotted that point. So what about at x equals, I don't know, let's go to 2. So at x equals 2, maybe I'll make a little table up here. So at 0, I got 0. At 2, plug in a 2, we get -4 plus 12. So it looks like a +8. Okay. Let's see, maybe I'll go to 4. Oh, let me plot that point first. So I had the point 2, 8. So 2, 2, 8. So now at 4, plug in a 4, I have -16. So -16, and then plus 6 times 4, which is 24. That's +8. So over here, right here again. Let's go out to 6. So at 6, we have -36 plus 36. That is 0. So over here, I would have a 0. If I wanted to figure out where the vertex is, I can take the derivative, right? F prime of x equals -2x plus 6. Set this equal to 0, right? Because the vertex will occur at a local. Solve this, it looks like a 3. Naturally, it's a 3. Oops. Because, well, right in between these 2 points, there's a 3. And by symmetry, I could tell that the vertex should be at 3 there. So let's plug in a 3 just to see where we end up. So we got a 0 there. For 3, plug in a 3, we get -9 plus 18, right? That looks like a 9. So right here at 3, which is right in the middle of 2 and 4, I'll be right in the middle of 8 and 10. So I'll go ahead and draw this part of the parabola here the best I can. That's not great, but that'll work. For the other one, I'll go ahead and make another table for it. So we get a 9, by the way. So this was our table for F. Let's maybe do a table down here for G. So at 0, plug in a 0 and we get a 0. So I'm just further darkening that point. At 2, plug in a 2, we get a 1. 2, we're at 1. Okay. Now at 4, plug in a 4, we get a 4, right? 4 squared, 16. 16 over 4 is 4. So 4, 4. Let's check out what 6 is doing. 6 would be 36 over 4. My arithmetic is bad today. That's a 9. So 6, 9, right about there. So I'll go ahead and draw this now, because it looks like we have an area that's now defined. Okay. So although it wasn't stated to like find this specific region, this is the only region that is fully enclosed by these two curves. Okay. Also, what's notable about this region is that for all x in this interval, f is above g, right? This is f, and this is g. So that means I need to integrate to find the actual area. I need to integrate using this formula here. So I'll have negative x squared. Maybe I'll write that in dark blue just to highlight this. Plus 6x, right? That's our upper, minus the lower. All right, there's my upper and my lower again. The thing about it is we need to figure out where these limits are. So for sure I can see that the functions are equivalent right here, so that means my lower limit would be 0. To find my upper limit, I'll set the functions equal to each other and solve. So I'll make a little note here. Need limits. So we need to solve negative x squared plus 6x equal to x squared over 4. So maybe I'll bring this over here. So I'll subtract x squared over 4. So just to stick with one color now, we have negative, so this would be 4/4, so this would be negative 5/4 x squared plus 6x equals 0. Solving for x. So factor out x. That leaves a negative 5/4 x plus 6. So we're getting one of our answers from 0, but I already knew 0 is an answer. So the other answer is the one coming from here that I care about. So we need to figure out when negative 5/4 times x plus 6 equals 0. So in other words, x equals negative 6 over negative 5/4. I'll type that in my calculator. So 24/5, which is about 4.8, which is reasonable. Okay. I'll just use 4.8. That's kind of nice. So that other limit is 4.8. Okay. So here is what we need to integrate to find this exact area. So combine like terms. Right, we have negative 5/4 x squared plus 6x from 0 to 4.8. Find the antiderivative. Oops. So all I did there was I combined these like terms. So I'm still integrating this. So this would equal, so I raise the power by 1, that'll be a 3, divide by that new power. So that ultimately will be negative 5/12 x cubed. Same kind of thing here. We raise the power on x by 1 to get a 2, divide by that new power. So I'll have plus 3 x squared, evaluating from 0 to 4.8. Okay. Since everybody involves x as a multiple, 0 is not going to produce anything. So what this now amounts to is evaluating at 4.8. So negative 5/12 times 4.8 cubed plus 3 times 4.8 squared. 23.04. And that would just be some square unit. Keep in mind you can check your work if you have this type of calculator, that is. So if I integrate, just to check this one, maybe down here. So if I integrate from 0 to 4.8, and then we have this function negative 5/4 x, maybe I need times, x squared, and then plus 6 times x. Let's see what that results in. Same thing. Okay. Let's try another one. So sketch the curves. I'll go ahead and do that. So for y1, we would have a y-intercept of 10, and then this thing is going to open down. Just some quick math, it'll have x-intercepts of root 10 and negative root 10. That's going to be a little bit more than 3 and a little bit more than negative 3. Right, if you set this equal to 0 and do all that fun stuff of solving this. Right, so what I'm doing there is imagining 0 equals 10 minus x squared. Then x squared equals 10. So x would equal plus and minus root 10. In other words, over here, at a little more than negative 3, we'll have an intercept. And then over here, a little more than positive 3, I'll have an intercept. So maybe I'll just draw that. Beautiful. Okay, then the other one, maybe in red. So this one, it looks like it has a negative 6 y-intercept. And then kind of similar thinking, the square root of 6 will naturally occur as x-intercepts, right? If you think 0 equals x squared minus 6. So 6 equals x squared, blah, 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 plus and minus root 6 equals x. So that's about 2.5, a little less than 2.5. So over here, a little less than 2.5. A little less than negative 2.5, I guess, technically a little more. All right, and then up, up. Not the best parabolas I've ever made, but that's okay. So we must be looking for this area. Right? So for this interval, y1 is always above y2. So what that means is we need to integrate y1, I'm writing things down here, sorry about that, minus y2 dx, and then we need to figure out where these things are intersecting again. We still need to figure out what number goes here and what number goes here, right? So we still have this to figure out. So to do that, we set y1 equal to y2 and solve. So I'll go ahead and do that. So 10 minus x squared equals y2, which is x squared minus 6. Solve for x. So maybe I'll add x squared, and I'll also add 6. So 16 equals 2x squared. Divide, solve for x. So 8 equals x squared. In other words, plus and excuse me, plus and minus the square root of 8. So x would equal plus and minus 2 root 2. Right, square root of 8. So that tells us our limits. Got something in my throat all of a sudden. Hold on. Didn't get my water. All right, so one thing we could do is we could now go from negative 2 root 2 up to 2 root 2. But we could do something even more clever. Notice the region is symmetric. So what I mean by that is this half, that area is exactly half of the other side. So this integral would be equal to the integral, if I double it, from 0 to 2 root 2 of, again, still y1 minus y2. So I'm going to choose this option actually. I'm going to double it, use the 0. It's kind of nice to plug in 0 instead of negative 2 root 2. So this would equal, now actually plugging in the functions. So we'll have 10 minus x squared minus parentheses, right? Because I need to subtract all of y2, which is x squared minus 6 dx. Combine like terms, integrate, right? All that good stuff now. So 2 times the integral from 0 to 2 root 2 of, so this is going to turn into positive 6, and then I'll add that to 10 to make a 16. This is going to turn into negative x squared, add another negative x squared. I have negative 2x squared dx. You can factor constants out of integrals. So I can say this is exactly equal to, if I factor out a 2, I'll multiply that 2 by this. So I'll get 4 from 0 to 2 root 2 of the integral 8 minus x squared dx. So actually finding an antiderivative now, I'll have 4 times 8x minus 1/3 x cubed, integrating that from 0 to 2 root 2. Keep an eye out for this. Since I have a 0 and everything is a multiple of x, remember if I had 8 raised to the x, it wouldn't zero out. That would be a 1. But since everybody is a multiple of 0, then that bottom limit just vanishes, right? Nothing will be produced there. So this amounts to finding 4 times 8 times 2 root 2 minus 1/3 times 2 root 2 cubed. All right. So simplifying that, so I can write 30, well, even 32 times 2, so I'll write 64 root 2 for this combination, and then I'll have minus 4/3 right, the 4 times the 1/3, and then 8, so times 8 times, I guess this would be 2 to the 3/2. Do I want to write it that way? I'll say 2 cubed and the square root of that. So I'm just trying to figure out how I want to leave this answer at the moment. Let's see. So I'll just leave it in exact form as 64 root 2 minus 32/3 times the cube, or sorry, the square root of 8. The cube root of 8 is the same as 2 root 2. So if I just simplify that now, 32 over 3 times root 8. This is the same as this, so we'd have 64 root 2 minus 64 root 2 over 3. So that will leave 2/3 of 64 root 2. So I'll go ahead and write that down in a second. So 64 times 2 and then divided by 3. All right, so in the end, I'll write it up here. So it goes from here to way up here. This is 128 over 3 times root 2 square units. That would be the exact form of this area. Let's see what that answer is, approximately. So 128 over 3 root 2. It's about 60.33. If I check my work, I'm going to go back to this integral right here to check my work. So I'm assuming that my work was okay up to this point. Okay, so 2 times the integral of 16 minus 2 times x squared, and then 2 root 2, 0. Let's hope for about 60.33. Yeah, good. But unless otherwise stated, right? Unless otherwise stated, leave your answers in exact form. All right, I'm skipping ahead to an application. So example 8, this is on page 131. So it says the rates at which rain fell in inches per hour in 2 different locations t hours after the start of a storm are given by these functions. Compute the area between the curves for 0 to 2, and that's apparently 2 hours, and interpret your result in this context. All right, so what we need to do is graph. We actually don't need to graph, but I'm going to, just to kind of get a visual thing. I'll do this first one in blue. So it looks like if I have maybe a table in blue here. So this will be T, this will be F. And then maybe over here I'll start a table in red. This will be T, this will be G. So let's pick some numbers. So for 0 time, there was apparently already some rain on the ground. So it looks like 0.6, right? Plug in a 0, we get 0.6. So I'll graph that. So this is my time axis. This is my F/G kind of Y axis. And then 0.6 right there. Okay. What about, let's plug in another time. Let's see at 0.2 what we get. So I'm going to plug that in now. So 0.73 times 0.2 cubed minus 2 times 0.2 squared plus 0.2 plus 0.6. My calculator doesn't like that. Let's try all that again. 0.73 times 0.2 cubed minus 2 times 0.6 squared plus 0.2. I'm having a lot of calculator issues at the moment. Let me clear all that off. Let me just show you what I'm doing. 0.73 times 0.2 cubed minus 2 times 0.2 squared plus 0.2 plus 0.6. Please give me a number. All right. So about 0.72 blah, blah, blah. I'm going to graph that at about 0.7. Let's go out to 1. Let's see what's happening at 1. So I did that at about 0.7 for this one. Let's go out to 1, see what's happening there. So if you scroll back left, you can just replace all these 0.2s with 1s. So about 0.33. Okay, so I'll graph that. At 1, it's a little more than 0.3. Right about there. Let's see what's happening, I don't know, over here at 1.6, and then I'll probably do 2, and I'll call that good. So I can go back and change all these 1s to 1.6s. So 0.07, a little bit below 0.1. So down here at 1.6, it's a little bit below 0.1. And then let's try 2. This is about 0.07. And now change those 1.6s to 2s, since we're looking for the first 2 hours, right, this part. So I'm going up to 2. So 11/25, about 0.45. It's 0.44. So a little bit less than 0.45. So over here at 2, about 0.5, a little bit less though. Okay, so I'll go ahead and draw this curve. We have this essentially going on. All right. Okay, for the other one, I'll go ahead and pick the same t's. So maybe 0, 0.2 again, 1, 1.6, and 2. We'll just do those. All right, so it looks like for 1.1, or sorry, for 0, we're gonna go at 1.1 here, right? So plug in a 0, we get 1.1 in G. So I'll go ahead and plot that. We have 1.1. And now at 0.2. So I'll go ahead and use the calculator now. So 0.17 times 0.2 squared minus 0.5 times 0.2 plus 1.1. A little more than 1. 0.2. Oops. So right about here. Let's call that good. So about 1. I'll just say there. At 1, so now go back, turn these 0.2s into 1s. So about 0.77. Well, exactly 0.77. So almost 0.8. Right about there, I'll go ahead and change the 1 to a 1.6 now. Doing 1.6. .73. Okay. I'll just call it about 0.74, if you can see that. I can't even see that. So about 0.74. So 1.6, 0.7. It's getting difficult. 6, 7, right about there. And then finally 2. Let's plug in our 2. And then just like that, we'll have the graph. So 0.78. Okay. So here is this curve. All right, so what we're doing, if we want to compute the area between the curves, and that's what our goal is, then we're looking for this area here, again, from 0 to 2. Okay, so it looks like G, which is our red one, is totally above F for the entire interval that we care about. So we'll just need to do one integral where we have G minus F. So the integral will go from 0 to 2, right? We don't really have to figure out any intersection point, luckily here. It's just kind of cut and dry. And now G, 0.17 t squared minus 0.5 times t plus 1.1, and then minus f, since it's on bottom, right? So I'm looking here and here. So parentheses, 0.73 times t cubed minus 2 times t squared plus t plus 0.6. And then everything is being integrated with respect to t. So simplify, combine like terms. Right, so I'll have, it looks like just 1 cubic, so I'll go ahead and write that out front. So negative 0.73 t cubed. So this one's accounted for. Then I'll have these squared terms. This one actually turns into a plus, right? So that'll be positive 2 t squared. So I'll have plus 2.17 t squared. Right, these ones are now accounted for. The t's, so this will be negative t, right, once that negative comes in. So negative 1.5 t, right, these ones are now accounted for. This negative, again, will distribute to 0.6. Then I'll combine that with 1.1. So I'll have 1.1 minus 0.6, which is 0.5 or a half. So plus 0.5, everything with respect to dt. All right, just to save a bit of time, I'm gonna use the calculator. So integral, I'll go ahead and type this in. So negative 0.73, I'm going to use x, right, because the differential operator here is with respect to x, so I have to reference that variable. So plus 2.17 times x squared minus 1.5 times x plus 0.5, and then we're integrating from 0 to 2. So this is equal to 0.86, and that 6 repeats forever. This would be, so our functions were amount of rain in inches per hour. So this would be the amount of rain in inches. But we also wanted to interpret this. So what the heck does that mean? So if we look at our graph, if this is the area, then it rained this amount more at location defined by function g as compared to location as defined by function f. So I'll go ahead and summarize that here. So it rained 0.86 inches more at location defined by function g as compared to the location defined by function f. So that interpretation is needed also, right? We were to compute, that's the number, and then we were to interpret, and that's all these words. Okay. All right, moving on to 6.2. Sorry, I had to take a little break. But moving on to volumes by slicing, right? When we're getting less uncomfortable with finding areas, we're all of a sudden going into finding volumes. I encourage you to leverage geometry to try to make sense of these upcoming formulas because they are very, very geometric. It's kind of packaged in a calculus wrapper, but it is geometry really at its fundamental core. So here's a basic picture of what is meant by a solid of revolution. So imagine we had this problem from before, and we could find the area under that curve. If we integrate root x from 0 to 1, we could find that area. But imagine if that section of area under the curve were then rotated specifically around the x-axis, right? If you rotate around the y-axis, you'd get a completely different shape. But rotating around the x-axis, we tend to get this shape here, right? So what is going on? Basically, there is a disk, this disk here, that is produced if you imagine rotating just this rectangle. So if you imagine rotating just this rectangle here, what is produced is this disk within this larger three-dimensional object. The volume of that disk will inform how we find the volume of this more strange object, okay? So if you think about the volume of that disk, it will depend on R. So the volume of that disk would depend on the radius of the disk, right? Notice though that the radius, it changes, right? If I'm over here and I just identified this sliver in that disk, then this would be my radius, and it increases as x increases. So the radius is not fixed. But if I look specifically, let's say this is 1/2, the radius of that then generated disk at 1/2 would be the function's value at 1/2, right? The radius here would be simply the function value. To find a volume of a cylindrical disk, such as this, we usually square the radius. So I'll go ahead and write that radius needs to be squared. And then we typically multiply by pi. And then by some width, right? So to get the actual volume, this would just be the area of the circle, right? This would just be this area. But then to multiply and get volume, I then multiply by delta x. So I multiply by delta x. In the integral, notice what we have. So the volume of that disk is given by this, but the volume of the actual shape that we cared about would actually require an integration from 0 to 1 over the function squared times pi times dx. So this is acting like delta x. It's a small sliver of a change of x. So hopefully you can see embedded within this volume formula, within this integrand, is simply a volume formula from geometry, right? So pi times r squared times the height of the cylinder. So if you actually carry this out, here's me carrying this out now. Here's a worked example. So to find the volume of this thing that I'm pointing to up here, this actual thing, the full-on volume, not just the disk, but the full-on volume of this solid, I would integrate from 0 to 1 pi times the function squared, right? Here's the actual function itself, root x. That's the function along this curve. Right, so this is the root x that we're integrating through. We square it, and then we multiply by dx. So what you can do is you can pull out the pi. So pi can come out front. It's a constant. Root x squared just leaves x. Technically absolute value of x, but from 0 to 1, we're just fine writing x. And integrating. So raise the power of x by 1. We get x squared, divide by that new power, then multiply by pi. So I get pi over 2 times x squared, then evaluate the second fundamental theorem of calculus, the upper minus the lower. So here's the upper minus the lower, and then times pi over 2, we get pi over 2. And that would be cubic units. So that would be the volume of this strange object. You might call this a paraboloid in the future. Let's try one. Here's a slightly different one. So I'll do a couple of these. I'm not going to do every one though. You can check the key for sure. So let's see what this one says. It says find the volume of the solid obtained by rotating this region, y equals x cubed, y equals 8, and x equals 0, about the y-axis. So instead of rotating around the x-axis like this previous one, we're rotating around the y-axis. So that's what this kind of arrow represents. They told us these different segments. So the y equals x cubed is this one. That's this piece, right? Of course it continues on this side. The y equals 8 is this one. And then the x equals 0 is a way of actually enclosing this region. So this is the region we care about. when it gets rotated around the y-axis, you can see that this shape, if you kind of just turn on your imagination there, that would be generated. Okay, so our job is to find the volume of this solid, right? So just to remind us, this is using what's called the disk method. Okay, I don't know that I used that language before, but right now we're learning about the disk method for finding volumes. In a second, we'll be learning about the washer method. Because this little imaginary segment, so just to explain why this is a disk and not a washer, that segment is literally attached to the axis of rotation. So when this gets generated and actually rotates, it does not generate a washer. This is like a solid disk, right? So it generates like a pizza rather than a donut. So that's why this is in this disk method section. So what we need to do, by the way, since this little sliver is pointing at the y-axis, this means to me that everything needs to be with respect to y. Okay, so my formula was the volume would be equal to this integral from a to b of pi times the function of x squared times dx. In this case, so that everything gets transferred to y, the volume will be from c to d pi some function of y squared times dy. So these limits are y limits. They are not x limits. So I'll go ahead and do that now. So let's write this down. The volume of this, well, it looks like we'd be integrating in terms of y from 0 to 8. So 0 to 8. And then inside the integral, the integrand would be pi times our function. And here's our function solved with respect to y, right? We were given y equals x cubed, but we would need to solve for x there. So take a cube root of both sides. That's what's been done already. So we have the cube root of y equals x, and that's why we see that right here. So that is actually the function that we're integrating across. Okay? So it will be the cube root of y squared dy. So this is what we need to integrate. So this would be equal to pi. I can bring that outside from 0 to 8. I can think of this as y to the 2/3 and then dy. So actually finding the antiderivative now, I'll have pi times, well, raise the power by 1, I get 5/3, divide by that new power, so I'll have 3/5 y to the 5/3, and then evaluating from 0 to 8. Since everything is a multiple of y, the 0 is not going to produce anything. So I'll just evaluate at the upper limit. So 3/5 times, I guess that would be the cube root of 8, and then raised to the 5th power. So I'll go ahead and leave this in exact form. The cube root of 8 is 2. 2 to the 5th is 32. So we would get, I guess, 96/5 pi, right? So I get 2 to the 5th, 32. 32 times 3, 96. So 96 over 5, and then times pi. And this would be cubic units. Let's go into the washer method. So not in every case will the axis that you're rotating around be literally attached to the region that is being rotated. So here's a picture of what I mean by that. In those cases, we use not the disk method, but the washer method. And here is its formula. It comes again from geometry. And basically, if you had, like imagine you had a case where you're finding the area of like this washer here. So how would you do that? Well, it would depend on this radius. So there's like a larger radius there, and then we have this like smaller radius. So the actual true area, that red stuff, would be the outer one, pi capital R squared minus pi times lowercase r squared. So again, the radius is the function. So hopefully that makes some sense, right? Pi can be factored out. We get the larger radius minus squared minus the lower radius squared. And that's essentially what exists right here. Right here is pi factored out front. Here's the larger radius. The function is really defining the radius, right? This larger radius here would be defined by that larger function, right? This larger radius. And then that inner one is being defined by that inner function. So we would get this as our inner radius. The difference is the true area. When you rotate an area, you get a volume. Okay, so it says the region R enclosed by the curves y equals x. So here's y equals x right here. Y equals x squared, here's that one. And if we rotate that about the x-axis, it says find the volume of the resulting solid. So this is our kind of like little hypothetical chunk of area, and we're rotating it around this axis. So that naturally will create this washer, right, with the hole in the middle instead of a disc. So there's this open space there. Okay. So let's go ahead and write this down. So the volume of this would be, well, we integrate along the interval we care about, right? And this area is defined from 0 to 1. So I'm going to integrate from 0 to 1. By the way, this region is pointing at the x-axis. So that tells me everything with respect to x. Okay, so these are x limits. My functions need to be in terms of x. So it's the upper, it's the larger one, minus the lower one, right? The larger one squared, really, minus the lower one squared. So in this interval, the upper one is this x. So I'll have x squared, right? I guess I lost my pi. Let me write that out front. So there's that upper function squared, and then minus this lower function squared. So x squared squared. We have dx, right? And this would be defining the volume of this kind of strange conical solid. Okay, so let's go ahead and simplify, integrate, do all that calculus stuff now. So pi from 0 to 1, x squared minus x to the 4th dx. Finding the antiderivative, I would have pi times 1/3 x cubed minus 1/5 x to the 5th, right? We need to integrate that from 0 to 1. So everything is a multiple of x. So again, the 0 doesn't apply. Don't overly abuse that fact though, right? Because if this were 3 to the x and not x to the 3, 3 to the x evaluated at 0 is not 0. So you do have to be careful about using this, but it's true in this case. So we would have pi times 1/3, so 1 cubed minus 1/5 times 1 to the 5th. Let's figure out what that is. Two 15ths. So we would have 2 15ths pi. That would be cubic units. All right. I'll talk to you next time.